Hi, and welcome back to Science Geometry Unit 2, where your minds will be tortured to death through this boring course. Today in Unit 2, we'll be talking about mathematical modeling, or something. There's also inductive reasoning, logic, and all this stuff. Let's start with inductive reasoning. Inductive reasoning is the process of observing data, recognizing patterns, and making generalizations about those patterns. Usually it's used to continue patterns seen. There's usually trial and error, even though Ms. Choi says not to assume, but in case trial and error would include assuming. Doesn't make much sense there. And it also uses past experiences. So for example, let's say this day is sunny, and every day when it's sunny, it always ends up raining. If that happens every day, then if you see a sunny day outside, it's most likely going to rain on your day. Another part about inductive reasoning is that it uses discoveries by noting similarities. I don't know what that means, I'm just reading it off of this thing. And usually the generalized conclusion is called a conjecture. Don't know why they had to change the name if it's the same thing. And to disprove a conjecture, you only need one counterexample. So let's say it rains. So let's go back to that day about the sunny day thing. Let's say if it's sunny, if it rains every day, then you make a conjecture that it would rain every day if it's sunny. But let's say there's one day where it doesn't rain when it's sunny. Then in that case, your conjecture is false. And it also means that you were being very dumb about what you just said. The mathematical models, they usually use inductive reasoning to find a pattern in a sequence of numbers. The function rule is used to determine the nth term of a sequence. So let's say it is x squared. The function rule is used to determine. So let's say you have a table where it says if x is equal to 1, then y is equal to 1. If x is equal to 2, then x is equal to 4, and so on. Then to figure out n, then you just figure out the equation, which is essentially n squared or x squared. Usually when there's graphs or pictures of situations, then or when you write equations, then you can make a mathematical model. Function notation. Function notation is that little f parenthesis n thing that you see a lot, or f parenthesis x. It's that weird thing that you see instead of y. Talking about a waste of time. Who wants to write more stuff? Who wants to do work anymore? I mean, who does? Linear functions. Linear functions are functions that generate a sequence with constant differences. So if a linear function is just simply x, then the difference is just x, or 1. Deductive reasoning. The complete opposite of inductive reasoning. Deductive reasoning is the process of showing that certain statements follow logically from accepted facts. When you give a reason for each step in the process of solving an equation, you are using deductive reasoning. They use facts to prove statements, but it sounds like a heck ton of more work. Who wants to do more work? So, inductive reasoning is used to make conjectures. Deductive reasoning is used to verify conjectures. So, very boring. And I think that we are past this section. That we just passed the boring section. Now there's even more boring stuff. So good luck. If you can watch the rest of this video, I'll be very surprised. Conditional statements. A conditional statement is a statement that contains both a hypothesis and a conclusion. So it's kind of like science. Have you ever seen science in the past, like 6th grade, 7th grade, so on, with if, then, conclusions, hypothesis? Well, this is what you're doing here in conditional statements. So an example of this would be if I don't do my homework, then I will fail the quiz. Probably not true, being that I'm so smart, but that's an example. In logic symbols, there's a P and then there's an arrow that has 2 lines with no connecting thingy. So I'm not going to draw this out, it's too much work. in logic, there can be put as if P, then Q. P would be the hypothesis, which is the if part. Q is the conclusion, which is the then part. The converse of conditional statements. Converses of conditional statement, they essentially just flip around the part. They just flip it around. So it was if, original was if P, then Q. Then in this case, it would be if Q, then P. Q becomes the if part, and P becomes the then part. So it would be, if I failed my quiz, then I probably didn't do my homework. But that's a lie. I would never fail a quiz, because I'm so awesome. Biconditional statements. A statement in which the conditional statement and its converse are both true. So in the past two statements, the converse and a conditional statement, one way might be true, but if you flipped it around, it might also be false. Like I just explained, because I'm so awesome. So in this way, there's an arrow on both sides, pointing to both sides of the symbol. So if they uses the words if and only if, it can work like this. So it can work as this computer says, if polygons are congruent, then corresponding sides and angles are also congruent. It can work the other way around too, and it still be true. If corresponding sides and angles are congruent, then polygons are congruent. I don't see where the if and only if comes into that though. Inverse. Inverse is just saying the false part. So of a conditional statement, inverse of a conditional statement negates the original statement. Negates, you can probably infer from that it means the opposite, to make it negative. So in logic state symbols, it's like a negative P, conditional negative Q, which is read, if not P, then not Q. Which is saying, if I don't do well on my homework, then I won't do. If I did do well on my homework, then I will do well on my quiz, which is completely true. The contrapositive of a conditional statement is essentially both negates and is the converse of a conditional statement. So in logic symbols, negative Q implies negative P. If not Q, then not P. So if I did do well on my quiz, then I did do well on my homework. Again, very true for me. Probably not true for you guys though. And if we just finish that part, so now we're on to parallel lines and angles, and angle relationships, I mean. Transversals. Let's say there are a line that intersects two or more coplanar lines at different points is a transversal line. So let's say there's multiple lines. Let's say there's multiple lines in one. Let's say there's a parallel lines. It can be any lines, parallel lines, intersecting lines. As long as there's one line that goes through all of those lines, then it's a transversal. Corresponding angles. Angles are angles that occupy a like position. So let's say there is angle, let me get a piece of paper sooner or later. But let's say there's an angle A, B, and C. This doesn't have the D, so I'm just going to do it again. Then this one, and then here is, these are corresponding angles. This would be corresponding to A, this would be corresponding to B, this would be corresponding to C. Alternate interior angles. This is not going to be too easy for me to explain since I don't have any pretty pictures. Oh wait, I have a computer screen. I can show you this instead. Go away, shapes. Come on. Alternate angles, interior angles, say on this computer it says, they lie inside the lines on opposite sides of the transversal. So it would be like this. Here is here is 3 and 4, and here is a 5 and a 6. 4 and 5 are alternate interior angles. 3 and 6 are alternate interior angles. They are inside these two lines, yet they're on opposite sides of the transversal. That makes it so much easier for me to explain. Yay! Alternate exterior angles. Similar concept, different places. And different colors. Pink, pink, orange, orange. there's angle 1 and 2 and 7 and 8. 2 and 7 are both outside and on opposite sides of the transversal. So they are alternate exterior angles. 1 and 8 are also exterior angles. Alternate exterior angles, I mean. What was I thinking? I'm being stupid today. So, as I had just said, they lie outside the lines, the two lines on opposite sides of the transversal. Consecutive interiors. They lie on the same side of the transversal, but they are inside these two lines. So there's 3, 4, and 5, and 6 again. This time, 3 and 5 are consecutive interior, because they kind of, if you imagine there's another line here, it's kind of like inside of a shape. They're connected together. And here's 4 and a 5. Yeah, 4 and a 5. So a 4 and a 6, what was I saying? So here, these are also consecutive interior angles, except they're just on a different side. They are here and here. They're on the opposite side of 3 and 5. Consecutive exterior angles. This is going to be harder to explain, but the same concept, just different place. They're on the outside, so they're on the same side of the transversal here, but they're on the outside of these lines. So 1 and 7 are consecutive interiors, so that's here. And then 2 and 4, 8, which is connected right here. You didn't see anything. Stupid technology, you can't do anything right. Okay, we're on the last part of this lesson. Transformations and symmetry. I told you, this is a very important video. I warned you. I think I did, at least. It's your fault for watching it, though. I warned you. Going back to transformations and symmetry. There are pre-images and images. So, let's say I have a pre-image is an original figure. So let's say there is an image, this is the pre-image. Then, an image, apparently, is a location that has been after the change. So let's say I moved this somewhere else. This is the pre-image, and I moved it, let's say, here. So here. This would be the image. Before and after. And the new figure is denoted by using primes. The image is denoted by using primes. So let's say there was an A, B, C, D. A prime, B prime, C prime, D prime. I hope I put that in the right order. Otherwise, that would be a really, really bad mistake. Transformations. The transformations moves the pre-image onto the image. Usually there is also isometry. Isometry is also known as a rigid transformation. So there means there's absolutely no change in size. So this, the example I just did with these two board, whatever these things are is an isometric transformation. Translation and transformation. The translation type of transformation. Translation is what I just demonstrated. A pre-image is shifted to a specific distance and direction. So, like I just did, from here to here. And it is isometric. What I just did, though, was not what I just said. Yay me. So then there are examples of translations. I'm not supposed to read this. There is but I can read these. In words, you can explain transformations by saying move 3 units to the right or 5 units down or something like that. And then in algebra 1 you had there's an x, y that in some arrow pointing to an x minus some number and y plus or minus some number. Same thing with x. I meant to say plus or minus for x. In algebra 2, the vector, or aka the vector notation, you use these weird signs. They're kind of like the greater than or less than signs, eating up, and then there's some number inside. In the y, or if the number's negative, then you move in the negative direction. It's essentially this, without the x or y, and it's just different parenthesis kind of thingy. Rotational symmetry. This is a little bit different. It's a figure that is rotated about its center, and it maps onto the original. So And then the rotation is 180 degrees or less. Either it's clockwise or counterclockwise. So you can't do 181 degrees. Wow. To find the degrees of rotation, you need to divide 360 divided by the number of rotations that you had to get back to where you started. So I have a box right there. Let me be back here in a few seconds. This cake was a really good cake before this box got destroyed. So this box is a hexagon. So you see here, if I turn this here, it has 6 sides. 1, 2, 3, 4, 5, 6. Assuming that these are completely congruent. Let's say if I turn this here in rotational symmetry, I turn this on one side. 1. This is an example of rotational symmetry. 2, 3, 4, 5, and 6. And these are all the same. So this is 6 degrees of rotation. So 360 and divided by 6 is 60 degrees. So you need to turn this figure by 60 degrees to have it be congruent to the original figure. Now this thing on the other hand, since it has these weird things, you have to turn it one time to have it exactly the same. So it has, in other words, no rotational symmetry. Rotational transformation. I'm not gonna like this. This is boring, even for me. I'm sorry, Miss Troy, but it's kind of true. The pre-image is turned around a specific point on a certain number of degrees, clockwise or counterclockwise. It is also an isometric kind of form. Now, it's essentially, this is the rotation that you would normally think of. So, if I had, which I do not have, I'm just going to use this board again. So, let's say this board here, and then a rotational symmetry. So, let's say you have to rotate around this point here. Then it rotates around any way that it says. 90 degrees. Let's say 90 degrees clockwise. This would be 90 degrees. Let's say it was from here again. 180 degrees. From here. And so on. But then we can also do counterclockwise. I shouldn't have thrown that away. Let's say around here at this point. Counterclockwise. So let's say 90 degrees. That's around 90 degrees. And you get the concept, I guess. Reflection or line symmetry. This is a straight. It's essentially trying to figure out lines of symmetry. It's when a straight line divides a figure into 2 mirror images. So try and find the reflection line symmetry of this box. You can't see. Don't read this right away. I should have given you enough time to think. So there would be, you can split it from here, 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 or here. If you thought out of the box, you could do it from here too. Out of the box. What we're doing with boxes. So that had a total of, I'm going to count this again. 1, 2, 3. If you were just looking at the one hexagon side, then a total of 6 symmetrical sides. If you were thinking out of the box, then 6, I guess. No, 7, I guess. And I'm not sure if a 3D figure will count though. Let's just say it doesn't. Then it will just be 6. Reflection transformation. A pre-image is flipped over a line of reflection. So this board, I just put it together. I'm a genius at figuring out how to put this together. It's isometric, but this is the perfect idea. So there's 2 lines. Let's say the middle of my face is a reflection line. Then this, if I had this figure here and I rotate it, then it would be around here. Like my ears, my big old ears. It's an isometric change, by the way. This is very boring. I'm starting to die. You can reflect it over any axis, any kind of line actually. You can reflect it essentially over, you can reflect it over the y-axis, you can reflect it over the x-axis, you can reflect it even over y equals x line. And you can also reflect it over, let's say, y equals -5 or x equals 2 line. You can also reflect it over those lines. Oh. Composition. I don't know what this means. Let me see what that means. Compositions are when two or more transformations are combined. So a reflection and a reflection, a translation and a reflection, or a reflection and a rotation, and I don't want to go for any more of these. They are isometric. The order of certain transformations matters. So let's say you had a translation and a reflection. If you had done a reflection and a translation, then you would have gotten a completely different result. And we are finally done. If you manage to survive all of these videos, I am very surprised. You deserve a reward. But I'm too mean. I'm not letting you have a reward. Who gets a reward for watching videos? My gosh, you guys need to get a life. So that's the end of my video, and I guess I'm just gonna go and get a cup of coffee. See ya.